Like we're ready. All right, so it's my pleasure to welcome Jason Emanuel George from the University of Georgia here. We'll talk today about Christoffel words and associated algorithms.
Good afternoon, everybody. I'm Jason. I am a master's degree student here. My advisor is Dr. Chiskovsky. And today I'm going to share some of our work on Christoffel words and some associated algorithms. So here's an outline of what we're going to hit today. We're going to start with a definition of Christoffel words. We're going to move to Christoffel morphisms. Discuss standard factorizations in the Christoffel tree. We're going to discuss the Burrows-Wheeler matrix, continued fractions, and calendar systems. And sprinkled in, there are 4 algorithms that we have which produce Christoffel words or their conjugates. So we're working in the space of a free monoid on 2 letters. So we have 2 letters X and Y. And basically, we're working with a group without inverses. So we have associativity and identity. We can create words using concatenation. We can just put X's and Y's together. As you can see, we have X, Y, X, 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 Y, Y is in the free monoid on X and Y. And then we're going to define 2 words to be conjugate if, say, W1 equals UV and W2 equals VU for some VU in the free monoid. And basically what that means, we can just cycle through the letters in a word. That gets us our conjugates. Notation thing here, the reversal of a word, W equals C1 to Cn, is denoted as W twiddle. Just put the letters in reverse order. Definition of Christoffel words. So we're going to have A and B be relatively prime, non-negative integers. They'll be consistent throughout the presentation. And we're going to want to look at the line of slope B over A in the Cartesian coordinate plane. And we're going to define the lower Christoffel path of slope B over A as the path on the Z by Z integer lattice. So if you look, we have that grid. That's basically our Z by Z integer lattice. The red line here is our line of slope B over A. This is just an example, of course. And we want the path to lie under the line of slope B over A, but we want it basically to be as close as possible to the line. And to do that, we just say there's no integer points in this region bounded by the path and the line of slope B over A. Better put that here. So then we construct the lower Christoffel word, slope B over A, by encoding the path as a sequence of unit steps. So we denote any horizontal steps as an X, any vertical steps as a Y. You just go in order from the origin to the next intersection point. This is the point A comma B right here. In this example, that would be 5 comma 7. And you just go in order and, yeah, assign each step a letter. So we got X, X, Y, X, Y, X, X, Y, X, Y, X, Y. So that would be our Christoffel word. You can define upper Christoffel words in a similar manner, just by taking it to be the path above the line. Christoffel words are primitive. So primitive basically means that it's not a power greater than 2 of another word. So we have W as a Christoffel word. And if we have some U to the K that's equal to W, then the K must be equal to 1. And that is a consequence of the fact that A and B are relatively prime. So you could imagine if, say, we were taking whatever point this would be, would that be 4 over 6? Obviously 4 and 6 aren't relatively prime. You can imagine the line that we're going to connect from the origin to there would intersect this point right here. Then we would get a Christoffel word down here, X, X, Y, X, Y. Then we could get another Christoffel word up here, X, X, Y, X, Y. It's the same word. So that would mean that that Christoffel word would be X, X, Y, X, Y squared, which can't happen because A and B are relatively prime. Yeah, we have two trivial Christoffel words. We're going to call X the Christoffel word of slope 0, so that's when B equals 0 and A equals 1. And Y will be the Christoffel word of slope infinity by convention. That's when B equals 1 and A equals 0. We're going to define the label of a point, ij on the Christoffel path, to be this number right here, IB minus JA over A. And this number is also the vertical distance between that point and the line of slope B over A. So as you can see down here, this example, we have, looks like 5 over 4. Down here, our label is 0 over 4 because we're actually intersecting the line. And then, as we move along the path, you can see the label changes, denotes the distance. So like up here, we have a point with label 8 over 4. So obviously that point's two units of distance from the line vertically. Move up to the next point, we got 4 over 4. So if you have any pairs of consecutive points on this Christoffel path, you take their labels, then they satisfy this inequality, or not inequality, excuse me, congruence right here. T is congruent to S plus B mod A plus B. Moreover, T takes a value each of 0 to A plus B minus 1 exactly once as T ranges over all consecutive pairs of labels. Basically, what that means is that the labels are unique within a Christoffel path, right? So you can see if you go in and check, we got 1, 2, 3, 4, 5, 6, 7. Yeah, they're all here. We will use that fact later. That is also another consequence that's guaranteed by relatively prime nature of what we're working with. So here's our first algorithm. We call it the basic algorithm. You just start with an empty word, and then you just basically check the label at that point on the Christoffel path. If the label is greater than 1, you append a Y. If it's less than 1, you append an X. And you just repeat until K equals A plus B minus 1, which is the number of steps you will have on the path. Yes, basically it just goes along the path. Okay, here, obviously less than 1, so we append an X. Here are labels 5 over 4, so we append a Y. Here's less than 1, so we append an X, so on. Next up, we have the intersection characterization, which is a different way to characterize Christoffel words. So basically what you have is you have the line segment of slope B over A from the origin to A comma B. And you're going to let Z be the Z by Z integer lattice. And you're just basically going to take the points which that line intersects the Z by Z integer lattice. And then you're going to order them basically from the origin to point A. So here, these 3 points right here are int AB. So our points, this red line intersects the Z by Z integer lattice. And basically we can correspond these points to the steps on the Christoffel path. So we have, if the point is, the X coordinate of the point is an integer, that corresponds with an X. The Y coordinate is an integer, it corresponds with a Y. You can kind of see how that works. Like if the line passes through, if the point has Y coordinate an integer, the segment next to it must go between 2 points with the top point having a label less than 1, right? And then to actually get the Christoffel word, you have to take that word you get from the correspondence here and add an X to the beginning and the Y to the end, because those intersection points are where the path actually intersects the line. So we just exclude them and add them on at the end. Moving on, we have Christoffel morphisms. So Christoffel morphism is an endomorphism on our free monoid. It just sends Christoffel words to Christoffel words or conjugates of Christoffel words. And this is our notation for how we define them. Because they're endomorphisms, we can determine any Christoffel morphism based on how it transforms X or Y. So we just denote that like so. We have G of X, G of Y. See an example of that here. So we have our 5 morphisms. These are basically the 5 basic morphisms. Turns out these will be all we need. They will generate the monoid of Christoffel morphisms. In particular, these 2 right here, G and D twiddle, excuse me. So we want to show that these are Christoffel morphisms. Pretty easy to show that they are injective.
I'm sorry.
Yeah.
What's the notation for the morphism? Sorry.
So basically the left coordinate takes X to that word and the Y coordinate takes this. Yeah. So like for G here, if you have a word like XY, it would take that to X, XY. You take the X to X, the Y to X. So for G and D twiddle, it's actually pretty simple to prove that they take Christoffel words to other Christoffel words. Specifically, G takes Christoffel words to the Christoffel word of slope B over A plus 1. D twiddle takes the Christoffel word to the one of slope A plus B over A. Basically, the way to prove that is you can define a linear transformation from R2 to R2. And you just define it like so. G of C comma D is equal to C comma C plus D. You can see in this graphic here, I have this Christoffel word is the one of slope 5 over 4. If you apply this linear transformation to it, obviously the line of slope 5 over 4 gets stretched to, would that be 9 over 5? And then the path also gets stretched. As you see, the X steps pretty much stay the same, but the Y steps are transformed into this diagonal right here. And then what you can do is then replace that with a movement XY, which corresponds to the function, how the G was defined as G takes Y to XY. You can see that right here. Take that to there. And you can do a similar thing for D twiddle. This is the same statement as the previous slide. It actually kind of works in reverse too. If you have a Christoffel word of slope less than 1, then there is a Christoffel word such that G maps that word to W. You can do the same thing with D if the D twiddle if the slope is greater than 1. For D and G twiddle, it's a little more. It's a different proof. It's a lot more technical. It's in the use induction on the length of W to show that they take Christoffel words to conjugates of Christoffel words. Basically, you do that by showing that if G takes W to XW and G twiddle takes W to UX, which of course that is UX is a conjugate of XW, and which is a Christoffel word. By the previous slides, we shown that G takes Christoffel words to Christoffel words. Yeah, same type of idea for D twiddle. So that shows that GD, G twiddle, and D twiddle are Christoffel morphisms. But what about E? So first fact we're going to need about E is that it takes lower Christoffel words to upper Christoffel words. That fact is pretty easy to realize geometrically. So if this is our lower Christoffel word here, E, if just as a reminder, basically just swaps the X's and Y's. So you just follow the path here, just say, and then just replace the X's and Y. So X here means a Y here. If you follow that, you get the upper Christoffel word. You can also think about it as a reflection across the line Y equals X in a similar way to how this was proven for G and D twiddle. The next fact we're going to need is that the upper Christoffel word and lower Christoffel word of given slope are conjugate. So here we have the Christoffel word of slope, so 2 over 3. And we basically extended that twice. So we actually have WW encoded here, where W is the Christoffel word, slope 2 or 3. And then you take the points that have maximum label. So maximum distance from this line. If you draw the line that connects those 2 points, you can see that the region enclosed by that and the Christoffel path has no integer points. And of course, it's a conjugate of the Christoffel word. So the upper Christoffel words and lower Christoffel words are conjugate. And those 2 facts together pretty much show that EW is an upper Christoffel word, which is a conjugate of a lower Christoffel word. So we have all 5 morphisms are Christoffel morphisms. Yes. The next fact that we're going to need is that the monoid of Christoffel morphisms is generated by these 5 morphisms. And we're going to use that to define the Christoffel tree later on. It actually turns out that you don't need D and G twiddle. Those are actually equal to conjugates of G and D twiddle with E. But we leave them in because it makes the proof easier. We're going to move on to the standard factorization. So you have your Christoffel word. We have all our labels, right? Earlier we found out that all the labels are unique within the Christoffel word. So you're going to take the point that has minimum label, which is 1 over A, and you're going to cut off the word right there. You're going to cut it in half, cut it in 2 pieces. So the path up to that point is your first word. The path after that point to A over A comma B is the second word. And we're going to call this our standard factorization. And so we can see here, cut it off at that point, we get the W is equal, the standard factorization is x, x, y, x, y, that first word here, and x, y for that second word. So the standard factorization actually uniquely factors W into 2 Christoffel words. And that being that if you just split W at 2 points, into 2 pieces, the only way to get 2 Christoffel words is to split it using the standard factorization. So now we have the Christoffel tree. We're going to use our morphisms that we talked about earlier. We're going to define a complete binary tree using G and D twiddle. So you have the root, which is X, Y up here. You're basically going to define any left branch is, you compose it with G, and a right branch, you compose it with D twiddle. And just a reminder that this is the function notation that we're using here. So this morphism would take the Christoffel word like XY to XY. This one would take it. This is G, this is D twiddle. And then basically, as you move down, you just compose G's and D twiddles. And a nice fact about the Christoffel tree is that it contains the standard factorization of each Christoffel word exactly once, which is quite nice because it means we can uniquely identify each Christoffel word as a series of compositions of G's and D twiddles. Finally, this fact is also quite nice. We have a Christoffel morphism, call it F, maps Christoffel words to Christoffel words if and only if F is equal to a standard factorization of a Christoffel word, which is quite nice because we in that case we don't have to worry about being conjugates. Being able to take Christoffel words directly to Christoffel words will be useful. And the idea of that proof is basically you just use the Christoffel tree to express F as a composition of G's and D's. D twiddles. Next is the box algorithm. I'm actually going to start with an example. We'll see the full thing written out later. So we want to find the Christoffel word of slope 5 over 9. So we have 9 X's and 5 Y's. Here's what we're gonna do. We're gonna take the Y's and we're gonna place 1 Y in a box. Okay, so we have 5 boxes, we throw a Y in each box. And then we're gonna take the X's and we're gonna distribute them evenly among the boxes, okay? So you go and you place an X in every box, you have 4 X's left over. So you just put 1 X in each box, so you have 4 boxes with an extra an extra X, and 1 box without an extra X, we'll call that B. So we end up with this, we got 4 boxes, A equals X, X, Y, 1 box B equals X, Y. Now you just repeat the process and you just replace the X's and Y's with A's and B's. So now we have 1 B, so we just put the B in a box. And then there's only 1 box, so you got to put all the A's in that box. So now you have a box C that has A, B in it. And then you unpack the boxes, so to speak. So we have C, we unpack that, we got 4 A's and a B, and then we unpack each of those boxes. So we get X, X, Y, X, X, Y, X, X, Y, X, X, Y, X, Y. That's our B right here. These are our A's, which is the Christoffel word of slope 5/9. This is the algorithm. Yeah, it's a lot. The interesting thing about this algorithm is that you actually have to kind of switch up which box, how the boxes work if basically if this remainder you get here in the division algorithm is greater than your B value minus your remainder value. And this step down here is us unpacking the boxes. So let's use our example again. We're actually going to go through the steps as they were in the previous slide. So you start with A equals 9, B equals 5. Okay. So we're going to set A0 equal to 9, B0 equal to 5. We're going to use our division algorithm. Okay. So we get, in that case, we get our quotient is 1, our remainder is 4. And because of our inequality, that's going to be, we get that the remainder is greater than B minus the remainder. So in that case, we'll go to, let's go back here. So what we just did, we found out that we're in this right here. So we'll go to this step, step 4, and we're going to basically define this H sub I as our morphism. So we're going to define our H sub 1 to be X comma X cubed Y of W. Then sorry, that's the second iteration. You always initialize the H0 with, see, it's up here. Sorry. So this H0 is what we get here in step 4. Once you get down to one of the A's or B's being equal to 1, then you have this base case here. That's what this H1 is. Okay. And then once you get there, you just compose the functions, apply them to this word X, Y, and you get the Christoffel word. So the box algorithm shows us that you can kind of think about Christoffel words as how can I evenly distribute these X's and these Y's across this word. Here's the Burrows-Wheeler matrix. You might have heard of the Burrows-Wheeler transform, which was originally used in data compression. And that did involve this matrix, but for our purposes, we don't really need the transform aspect of it. We just need the matrix. And what you do is you take your word and you take all the conjugates and you list them in lexicographic order, basically dictionary order. So here we got Christoffel word of slope 3/4, which is our first line here. Turns out the Christoffel word will always be the first line. You list all the conjugates, and you can see there's kind of some patterns here. There's like this cascading, these cascading x's that go down. There's like the y's that also cascade. Here's some properties of the Burrows-Wheeler matrix. We got the first and last rows are the lower and upper Christoffel words of slope b over a. So, right, we saw that earlier in the previous slide. Of course, our last row is also the upper Christoffel word. Two consecutive rows differ in exactly two consecutive positions. Specifically, they swap an x and a y. So we got our first row here, and our second row here. Obviously, they're all the same, except you just swap the x and y here, and that'll be consistent throughout the matrix. That's what kind of creates the cascading pattern that we see. The tth row of the matrix is a reversal of this guy, the a plus b minus 1 minus tth row. So you just take like the first row and the last row are conjugate. In this case, what it would be it would be the second and the second to last row. Sorry, not conjugate, reversals of one another. If you want, you can see that holds for all the pairs we have. And our last property is if you have the first row in this form, x, u, y, so you just sort of lop off the x, lop off the y, you got the u in the middle. The last row is y, u, x, so you just swap that x and the y at the end. So here's two properties that we're going to need later. So we have that if a plus b is odd, we get the middle row of the matrix is actually a palindrome. So we'll go back here, you can check middle row, yep, palindrome, nice. A plus b is even, you actually get the middle two rows are reversals of another, which we actually have by the previous property, but specifically we get that they also only differ in the middle two positions. So we have it written like this. The first row is the first of those two middle rows would be written u, x, y, u twiddle. So let's see what we got then. Yeah, x, y twiddle, and then the next row you just reverse it, but you still have u and u twiddle at the ends here. So you can see that matches up here and here. That kind of brings us into our next algorithm. So we're calling the nearest word algorithm. So basically you just set I and j to be 0. You let W be an empty word, and then you just run this check right here. This is all the same evaluations on either side. If you get the left is less than the right, then you proceed. You add an x. If you get it's greater than the right, you add a y. If they're equal, which only happens if a plus b or a plus b is even, then you can actually do either step 3 or step 4. And you just repeat that until I plus j is equal to a plus b. That produces a conjugate of a Christoffel word, not a Christoffel word. If a plus b is odd, the conjugate is a palindrome, which is our middle row, that Burrows-Wheeler matrix. And if a plus b is even, you get the two conjugates that were the middle two rows in that case. Yeah, so they're reversals of one another, which swap the x and the y. This is kind of the idea behind the proof. You can actually kind of see that this gives us the word that's kind of the average Christoffel conjugate, you could say. So here, this example is this for slope 2/3, right? So L is our line passing through the origin. We have L prime, which if you remember that the picture we had earlier where we showed the upper and lower Christoffel words are conjugate, we actually get that passes through that point of maximum label right here. So those are kind of our lines that define those two conjugates. And the conjugate you get from the nearest word algorithm actually intersects, you take the points that they start and end at, that actually intersects this line right here, which is exactly between L and L prime. So in that sense, you could say that these conjugates are the most average Christoffel conjugates. And that's for the odd case. For the even case, you actually do get you'll have two lines here. And either both words that you get will correspond to one of the two. Next up, we have continued fractions. So we're going to let A be a non-negative rational number, and we're just going to define the continued fraction representation like this. And we'll have the ith continuant be the rational number obtained from the sequence that's just up to I. Henry J. Smith, this is kind of one of the early papers on the subject of Christoffel words. He noticed this correspondence between continued fractions and Christoffel words and came up with this kind of recursive way to develop them. So you just basically take, it's a recursion. So you have your S sub I plus 1 here is equal to S sub I to the C sub I, which is one of your convergence to the S sub I minus 1. And for our two base cases, we have S sub minus 1 is X and S sub 0 is Y. And interestingly, from this, we actually get the S sub I plus 1 you get is actually not a Christoffel word, but it's of this form right here. It's either this form or this form where you have that middle chunk U and then a YX. But to get the Christoffel word, you just lop off the end there, place the X and Y around it like so. Here's an example. We have 8/3, which has these two continued fraction representations. We're just going to use this first one, the shorter one. So yeah, our base cases are always the same. You take the S sub 0, well, what's that first conversion? We got 2, so we square that. S sub minus 1, Y squared X. Just keep going so you get the word. Interestingly, you can see the end kind of flops between X and Y. So in this first S sub 1, it ends with YX. The second one, it ends with XY. The third one, it ends with YX. Actually, it turns out that will always correspond to the parity of whatever this I is. So if it's odd, it ends with YX. If it's even, it ends with XY. Next, we have the recursive continued fractions algorithm, which is basically just the way Smith characterized it, just in a different form. This form actually works directly with Christoffel words, so you don't have to lop off that chunk off the end. You always just have the Christoffel word. So you have your base cases here. If the continued fraction is empty, that we just worry about that for purpose of the algorithm. We just define that n equals -1. And then for n greater than 0, you just have, you just let Wn minus 2 be the Christoffel word, basically of this conversion right here. Wn minus 1 be the Christoffel word of this conversion. And then if they're even or odd, you just slap them together like this, right? To prove this, you just use the previous Smith's characterization, just use induction on the length of the word. Or not length of the word, length of the convergent. So let's do that example again with this method. So base case is here at -1, we have W1, W sub -1 equals Y. N equals 0, you got W sub 0 equals XY squared. So our first case n is odd, so we're going to have W0 to the C1 times W minus 1. Just, yeah. And at the end of all these steps, you will have a Christoffel word, which is quite nice. Here for the even, and here, you just flop the order of which previous convergence you use. So you use W0, then W1. You can kind of notice here that the W sub even stay on the left, and the ones that are odd stay on the right. So like this will always be W sub an even number. This will always be W sub an odd number. And in this example, notice we use the second representation here. We actually which ends with a 1. And because we have a Christoffel word here, W2 and W1, well, we raise that to a first power. Okay, so that actually gives us a factorization of W into Christoffel words. And because the standard factorization is unique, that must be the standard factorization. So that's another nice property of this, is that you can find standard factorizations using this specific representation. That's what this slide says. Yeah. The ordering of which convergence words you use changes based on if n is even or odd, but it's the same idea. So next, we're going to talk about periodic phenomena. This is also an idea that was kind of around since the start of the study of this topic. So basically, the idea is you have two sets. You have two relatively prime integers. You have this set of multiples of each up to so like here you have the set P, which is the set of I times P, such that I ranges from 0 to Q, and then same type of thing for Q. And you basically want to superimpose these sets in a sense, so you just intersect them. We're going to write that as A, and we're going to order them like here. You can actually correspond that to the word, to the Christoffel word, is what this theorem says. So in this case, the W1s are characters, letters, not words. So W sub I is X if the corresponding A sub I is in P, and it's Y if the A sub I is in Q. There's actually kind of a geometric argument to this. So you could think about dividing this line from 0, 0 to AB. You can think about dividing that. So like here, we have the word for 2 over 3. So in that case, our P would be 3 and our Q would be 2. So if you divide that line in half, that's for the Q over 2, you get this point right here. If you divide it in thirds, you can see that the division points will be these intersection points. And because of that, you can correspond with the integer, the intersection characterization, and get the Christoffel word. We're going to talk about calendars now. So that's kind of what the periodic phenomena kind of relates, how that relates to Christoffel words. So we're going to start with a Hebrew calendar. So it's a lunisolar calendar, which means it's based on lunar months and solar years. Okay. And basically, the intention of it is to keep the date of Passover, which is religious observance, on the first full moon after the spring equinox. So now you're thinking like, okay, so I want it to be as close to the spring equinox as possible. Obviously, it can't be before it. And it has to be that first full moon. So that kind of corresponds to that idea we had earlier, where that Christoffel path needs to be as close to the line as possible without going over it. But because we're working with months, we want to work within specific lunar months, and the solar years, those can't really be divided. They didn't want to divide those any more than that. So we had to work in those constraints. And because of that, the Christoffel word kind of naturally erodes. So when this was eventually standardized, it was a 19-year cycle. You had 12-month regular years and 13-month leap years on these years here. And if you correspond that to X's and Y's, so the regular years are X, the leap years are Y, you get this word here, which is not a Christoffel word, but it is a conjugate of a Christoffel word. Because of course the calendar loops, well, it's might as well be a Christoffel word because that's how it describes the relationship in that sense. But of course, these kind of calendars can't approximate the astronomical cycles of the sun and moon exactly. So before the system was standardized, like this pattern may be present sometimes, but there would occasionally be an extra leap year here or there. So when the system was actually standardized, because it wasn't able to fully account for the imprecision, I guess, of the astronomical phenomena, the calendar drifted. So they would have to throw in leap years here and there.
They actually threw in too many.
They threw in too many leap years?
Right.
Oh, yeah, I believe it.
That's.
All right, last we have the Gregorian calendar, which is a solar calendar. It's just based on the year. So obviously you guys probably know the rules for leap years. But you get the corresponding word. So X is just a normal year. Y is a leap year. And it's actually not a Christoffel word or a conjugate of a Christoffel word. Which kind of explains why the dates of equinoxes are kind of fluid. They can vary up to 3 days, I think. Like this past year, it was like March 9th, March 22nd or something like that. I think, but it can go as early as like March 19th. That was it.
Oh, I was just looking this up. I don't know very much about this.
Yeah.
Evidently, there's a lot of applications of these Christoffel words in like many different branches of mathematics. So like, there's this one for like geometric topology, where they're studying like Alexander polynomials. And they're defining these polynomials associated with Christoffel words. And showing that coefficient sequence is log concave. Other things. They seem to, this theory seems to come up a lot in terms of, Markov chains, geometric topology.
Yeah, I mean, these Christoffel operators that you find very early on, those and their invert, so like data generated, it's not a group because it's a monoid, but if you have their inverses, then they're basically like standard generators for SL2 or even less commutatively SL2Z, I should say, or even more. You can think of them as generators for like the automorphism group of free group on two elements. A little bit more non-commutative, and they geometrically correspond to, for group two generators, you think of like the plane with two punctures, and so you have loops in that space, and these generators correspond to like a Dane twist around the loop. So you kind of, Dane is a topological construction. Yeah, I think it's all beautiful topological story of what these things look like.
There's this thing called the strong box index. I don't know if this is where they run archive. This kind of things.
I don't remember being nearly eyebrow is that stuff, all of that's why it's stopping 2 letters. And you work with monoids of 3 letters. I don't know. I mean, I can see like geometrically,
Yeah.
it would be about underneath a plane, you work with a normal vector
Mhm.
that's slow, but I don't know about applications or theory, or even with like continued fractions, I don't even know what that would be.
Uh. Yeah, I don't know. I was thinking that like you could think about maybe like the integer lattice in 3 dimensions, like how would you even define?
We just
Like-
talking about movements, the
Yeah.
X, Y, Z. That's what I'm thinking like geometric,
Yes.
the line becomes a plane and you're working with a normal vector and the slope, but like, I don't know what applications I would have. I don't know if the theory would break down at some point or, you know.
Another direction you can generalize it is, so when you're drawing these paths, you're, you have this grid and you're connecting 2 points in that. But you can, there's sort of like a hyperbolic version of that. So I think of this grid as I'm taking a torus, so, kind of a circle across a circle, 2 different directions. If I unravel that in both directions, I get the plane. And the grid points are all of the images or pre-images of a single point. So I'm connecting 2 points on my grid that corresponds to a loop on my original torus. So these kind of lines they correspond to like elements of the fundamental of that torus. And you're counting somehow like these Christoffel paths you're kind of writing your element of the fundamental group as these 2 generating ones in an efficient as possible way. But you can kind of do the same construction if you have any surface, so not just a torus. You could, if you metrize it so that it's a hyperbolic surface, then you have a nice hyperbolic plane with some tessellation, and you can draw a line connecting 2 points, thinking of it as some loop in your surface, and then you can cross the different types of kind of the boundaries of these different fundamental domains, and that would be something like a hyperbolic Christoffel. So you could do this exact same story kind of on a hyperbolic tessellation.
Well, that's interesting because, let's see if I can get back. So you can actually like this Burrows-Wheeler matrix, you can actually kind of think about it wrapping around itself. So like this. So we talked about how the first and last rows just swap the X and Y at the end. Well, you could just think about, well, that connects that top row and the bottom row. And then, of course, because these Christoffel words, you can think about, they kind of loop if you just go beyond that initial line. So if you just keep going, they loop. So you could also think about connecting the ends, these sides of the matrix. So I guess in that sense, you kind of also get like a torus structure there.
Questions? Let's let the speaker get ready.
Nice.
Around 6, so if you send an email, the report, if you didn't, and
Songs.
It's now 3 letters.
Well, I think 3 letters would be much harder.
Yeah, I have no idea.
Hyperbolic,
Yeah. Actually, like,
track them on the way that.
Stephen would say like, that's all